Welcome to Calculus Volume 1. In this video, I'm going to talk about Section 2.2, the limits of a function. Before we begin, let's overview the learning objectives for this particular video. I'm going to show you how to use the correct notation to describe the limit of a function. I'm going to use table of values to estimate the limit of a function, or to identify when a function does not exist. I will also show you how to use graphs to estimate the limits of a function or to identify when the limit does not exist. I will define one-sided limits and provide examples. I will explain the relationship between one-sided and two-sided limits, use correct notation to describe an infinite limit, and briefly describe a vertical asymptote. Let's begin with the intuitive definition of a limit. Let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself, and let L be a real number. If all values of the function f of x approach the real number L, as the values of x, not equal to a, approach the value a, then we say that the limit of f of x as x approaches a is L. In brief, as x gets closer to a, f of x gets closer and stays close to L. Symbolically, we express this idea as the limit as x approaches a of f of x equals L. Problem-solving strategy. Evaluating a limit using a table of functional values. First, to evaluate the limit as x approaches a of f of x, complete a table of values extremely close to the value of a, but not equal to a. 2. Look at the values on each side of f of x around the value of x equals a. 3. If both columns approach a common value, then we state that the limit as x approaches a of f of x equals L. Using a graphing calculator or computer software, verify and look at the graph of f of x for values close to x equals a. Let's look at example 2.4, evaluating a limit using a table of functional values 1. Evaluate the limit as x approaches 0 of sine of x over x using a table of functional values. We will begin by looking at values to the left of 0 and approach 0, but are not equal to 0. We see that as x gets closer to 0 from the left, the functional values approaches 1. Now we'll look at x values extremely close to 0 on the right. As x gets closer to 0, but again not equal to 0, the functional values approach 1. So we would conclude that the limit as x approaches 0 of sine of x over x equals 1. Example 2.5, evaluating a limit using a table of functional values 2. Evaluate the limit as x approaches 4 of the square root of x minus 2 all over x minus 4 using a table of functional values. Here I have displayed the entire table. Notice on the left, as the x values get close to 4 but not equal to 4, the functional values approach 0.25. And as the x values approach 4 from the right, such as 4.00001, again the functional values approach 0.249 or 0.25. So we would say this is really close to 1/4. So we can conclude that the limit as x approaches 4 of the square root of x minus 2 all over x minus 4 equals 1/4. Checkpoint 2.4. Evaluate the limit as x approaches 1 of 1 over x minus 1 all over x minus 1 using a table of functional values. Pause the video and attempt this problem for yourself. Okay, now that you've attempted the problem yourself, let's look at the solution. Here's the table of values with x values extremely close to 1 but not equal to 1. Notice both the left and right approach -1. So we would conclude that the limit as x approaches 1 of 1 over x minus 1 all over x minus 1 is equal to -1. Example 2.6, evaluating a limit using a graph. For g of x, shown in figure 2.15, evaluate the limit as x approaches -1 of g of x. Figure 2.15, the graph of g of x includes one value not on a smooth curve. So notice as the values of x approach -1, the functional values continue to approach 3, but the function itself, g of 3, is actually 4. So which is the limit? Is it 3 or is it 4? Well, since the graph approaches 3, we would actually say that the limit as x approaches -1 of g of x is equal to 3, even though the function itself, f of -1, is equal to 4. So what's the significance of this? This example shows that the function value and the limit value do not have to match. The function is defined at one value, but the function values approach a different value. Checkpoint 2.5. Use the graph of h of x in figure 2.16 to evaluate the limit as x approaches 2 of h of x, if possible. Pause the video and attempt this problem. Now that you've attempted the problem for yourself, let's look at the answer. The limit as x approaches 2 of h of x is equal to -1. This time, the function isn't even defined at x equals 2. So this is also significant. This example shows that the function doesn't even have to exist, but the limit still can. Because again, it's just what does the function get close to? Theorem 2.1, two important limits. Let a be a real number and c be a constant. Then the limit as x approaches a of x is equal to a, and the limit as x approaches a of c is equal to c. We'll look at these further in the next section. Example 2.7. Evaluate a limit that fails to exist. Evaluate the limit as x approaches 0 of sine of x of 1 over x using a table of values. Here we see the table of values with x values extremely close to 0 but not equal to 0. On the left, the values oscillate or switch back and forth between positive and negative values and never seem to, what we say, converge upon a particular value. And on the right, the values mirror the left values, but they're the opposite as far as one's negative, one's positive. So these values never approach a particular specific value. So what do we say? Well, the function values oscillate and do not tend towards a single value. And the same is true for the right. In fact, they're the opposite side. So we would conclude that this limit does not exist. Let's look at a graph. So the graph of f of x equals sine of 1 over x oscillates rapidly between -1 and 1 as x approaches 0, and therefore it never goes to one particular value. So this limit does not exist. Checkpoint 2.6. Use a table of functional values to evaluate the limit as x approaches 2 of the absolute value of x squared minus 4 all over x minus 2. Pause the video and attempt this problem for yourself. Now that you've attempted the problem for yourself, let's look at the solution. Here's the table of values with x values extremely close to 2. Notice on the left, as x approaches 2, the values tends towards -4. And on the right, as the x values approach 2, but not equal to 2, the x values approach 4. So -4 and 4 are not the same. So from this, we would again conclude that this limit does not exist. Let's look at the graph of this particular function. You can see that on the left-hand side, we're way down there at -4, and on the right side, it jumps all the way up to 4. One-sided limits. Limit from the left. Limit from the left. Let f of x be a function defined at all values in an open interval of the form CA, and let L be a real number. If the values of the function f of x approach the real number L, as the values of x, where x is less than a, approach the number x, then we say that L is the limit of f of x as x approaches a from the left. Symbolically, we express this idea as the limit as x approaches a from the left of f of x equals L. One-sided limits. Limit from the right. Limit from the right. Let f of x be a function defined at all values in an open interval of the form AC, and let L be a real number. If the values of the function f of x approach the real number L, as the values of x, where x is greater than a, approach the number a, then we say that L is the limit of f of x as x approaches a from the right, and symbolically, we express this idea as the limit as x approaches a from the right of f of x equals L. Example 2.8. For the function f of x equals x plus 1 when x is less than 2, and x squared minus 4 when x is greater than or equal to 2, evaluate each of the following limits. A, the limit as x approaches 2 from the left of f of x, or B, the limit as x approaches 2 from the right of f of x. Again, we'll utilize a table. Here are the values close to 2 on the left. This we would plug into the top function x plus 1, so our values would tend toward 3. So we would say that the limit as x approaches 2 from the left is 3. Now let's look at the right side. If we plug in values to the right of 2 but extremely close to 2, we would be plugging into the bottom function x squared minus 4. Here we would see that the functional values approach 0. So we would conclude that the limit as x approaches 2 from the right of f of x is equal to 0. And that's exactly what we have, and here is how we would express it symbolically. Here is the graph of that particular piecewise defined function. Notice that as we trace along the graph coming along the left and approach x equals 2, we go up to 3. And if we jump over to the right side of the graph, then the functional values approach 0. The function itself is defined to be f of 2 equals 0. So left and right limits can exist, but here the function limit at x equals 2 does not exist. Checkpoint 2.7. Use a table of functional values to estimate the following limits, if possible. The limit as x approaches 2 from the left of the absolute value of x squared minus 4 all over x minus 2, and B, the limit as x approaches 2 from the right of the absolute value of x squared minus 4 all over x minus 2. Pause the video and attempt this problem for yourself to see if you've mastered left and right limits. Alright, now that you've paused the video and had time, let's look at the solution. The limit as x approaches 2 from the left of f of x equals negative 4, and the limit as x approaches 2 from the right of f of x equals 4. This is mirrored in that table that we had previously, because we've already looked at this function once. So the left and right limit exists, even though we found in that previous example that the limit itself did not. Here is the graph of that function again. Theorem 2.2. Relating one-sided and two-sided limits. Let f of f be a function defined at all values on an open interval containing a, with the possible exception of a itself, and let L be a real number. Then the limit as x approaches a of f of x equals L, if and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x equals L. In other words, if the left and right limit match, then the limit is just L. And if the limit is L, then the left and right limit will also be L. However, if the left and right limit do not match, then the limit as x approaches a of f of x does not exist. Recognizing an infinite limit. Example 2.9. Evaluate each of the following limits if possible. Use a table of functional values and graph f of x equals 1 over x to confirm your conclusion. A, the limit as x approaches 0 from the left of f of x. B, the limit as x approaches 0 from the right of f of x. And C, the limit as x approaches 0 of f of x. Let's look at our table of values. From the left, as we approach 0, our functional values get extremely negative. And as we approach 0 from the right, our values get extremely positive. So we would say that as we go to 0 from the left, it looks like we go to negative infinity, and as we approach 0 from the right, we go to positive infinity. And that's exactly how we would say this. Symbolically, we would say the limit as x approaches 0 from the left of f of x equals negative infinity, and then the limit as x approaches 0 from the right of f of x equals infinity. Since the left and right limits do not match, we would say that the limit does not exist. I would also like to say here that some books, instructors, professors, etc., would say that if the limit is infinity, the limit does not exist because it should approach a particular value. So here, you may have somewhere encountered that all three of these limits do not exist. However, some places also specify what type of infinite limit is it. Here's the graph to show you. Checkpoint 2.8. Evaluate each of the following limits if possible. Use a table of functional values and graph f of x equals 1 over x squared to confirm your conclusion. Pause the video and attempt these 3 limits yourself. Alright, now that you've had time to pause and try these yourself, let's look at the solution. Again, we'll approach 0 from the left. Our functional values approach massively positive numbers. It's actually square the amount from the last video. So that's going off to positive infinity. What about the right? Well, again, it's going to mirror the left because it's squared, so it's getting increasingly positive. So we would say that the limit as x approaches 0 from the left of f of x is infinity, or does not exist depending on your author of the book or your instructor. We would also say the limit as x approaches 0 from the right of f of x equals infinity, or does not exist depending on your instructor or the book. And in this case, they kind of match. The limit on the left and right are both infinity, so we would conclude that the limit as x approaches 0 is either also infinity, or we would say that it does not exist. Like I said, there is some ambiguity here in the writing. Example 2.11, behavior of a function at different points. I've made this little note that I've omitted parts from this slide from the textbook, and I highly advise you to go over to the textbook on openstax.com and look at the other parts of this particular problem. So use the graph of f of x in figure 2.21 to determine each of the following values. A, the limit as x approaches 1 from the right of f of x. B, the limit as x approaches 1 from the left of f of x. C, the limit as x approaches 1 of f of x. And D, the limit as x approaches negative 2 of f of x. Looking at the graph, you can see that as x approaches 1 from the right, the functional values tends toward 3. As we approach x from the left, the functional values approach 6. That means that the limit as x approaches 1 does not exist, since the left and the right are not the same. What about the limit as x approaches negative 2 of f of x? Well, that's 3. Because even though there is a hole there, the functional values still approach 3. So we would conclude that the solutions are 3, 6, the limit does not exist, and 3. Checkpoint 2.10. Evaluate the limit as x approaches 1 of f of x for f of x shown here. Pause the video and attempt this problem. Now that you've paused the video and tried this for yourself, let's look at the solution. The limit as x approaches 1 of f of x does not exist. The left and right limits are not the same. It doesn't matter what the functional values are in this case, because we don't even know them. It's just the point that the limits from the left and right themselves do not exist. So that theorem that we talked about concludes that the limit itself at x equals 1 does not exist. In summary, we've looked at what the big picture of a limit is. We looked at many examples to use a table to find the limit, and several examples from how to find the limit from the graph. We also talked about left and right-handed limits, and I kind of talked about limits at vertical asymptotes. In the next video, we will develop a deeper understanding of how to look at equations and quickly calculate limits.